Tyler, who is a professor at the University of Nevada, Reno, and the CTEMPS co-director. And I'll let Scott tell you about what CTEMPS is, but it's a shared use distributed fiber optic sensing facility. And he's going to talk to us a little bit more about CTEMPS and some of the great things that they do. So Scott, I'll turn the time over to you.
Okay, thanks. Can you hear me?
We can hear you.
Perfect. Okay. And I assume you can see my screen.
We can.
Good. Okay, thanks. Well, thank you, Brady, and all those organizing this conference. It's been a great morning, albeit a little bit early for me out here on the West Coast, but I had my coffee early this morning. So I just want to give all of you an update on what CTEMPS is. It's a distributed temperature sensing facility originally, and also talk about our DAS research coordinating network. And I want to highlight my collaborators on this, John Selker from Oregon State University with CTEMPS, and then Herb Wang and Casey Adderhold. Herb's at the University of Wisconsin, and Casey is at Iris Pascal for our work on the distributed acoustic sensing research coordinating network. Okay, hello. Let's see if we can get this. There we go. So what is CTEMPS? And by the way, CTEMPS stands for some relatively corny name of the laboratory that we came up with in 2009, which is the Centers for Transformative Environmental Sensing Programs. Which at the time, transformative was an important NSF word, so we used it in our proposal. We started in 2009, and we really were the first community user facility that was focusing on hydrology and hydrologic measurements. The hydrology community at NSF had long been clamoring for some kind of instrumentation facility, and we came along with the idea of bringing distributed temperature sensing, which was a well-known and well-used instrumentation in the oil and gas industry and the electric power industry. It was really kind of a new thing for the environmental community, the near surface Earth. And so our goal is to bring high resolution, both in space and time, surface Earth sensing. And you'll see we do some other things as well besides distributed temperature sensing. And again, it's a jointly operated, funded by the National Science Foundation at the University of Nevada, Reno, my home, Oregon State University, and also Smith College in Massachusetts. And we basically modeled ourselves after the successful instrument centers in earth sciences, Iris Pascal and UNAVCO. So you'll see a lot of similarities. We are just much smaller than they are. So currently, CTEMPS, we have a fleet of 11 completely field deployable distributed temperature sensing systems. And we have some higher resolution laboratory grade instruments that can also go out in the field, but just require additional power. We maintain a complete inventory of fiber, both single mode and multi-mode. We supply fiber splicing, supporting equipment, everything an individual or a team would need to use a distributed temperature sensing operation in the field. We maintain a data management system and storage of all data that comes in. It's freely publicly available as well. And since we started, we've supported about 200 distributed temperature sensing projects, and we've been able to work on all 7 continents with those. So this is just an image of what one of our instrumentation boxes look like. It's completely weather tight. All the data comes back by cell modem if you're within cell service. And we maintain the data for our users. It's completely self-powered, solar powered. And in this case, we're monitoring, researchers were monitoring a stream system in Northern California. And we've evolved from just distributed temperature sensing. We still focus on all aspects of fiber-based temperature sensing, as well as now you'll see a little bit of distributed acoustic sensing. We also, with that idea of focusing on high resolution space and time measurements, we've developed a UAS program that is available for the community to use. We focus on high resolution topography, hyperspectral imagery. The image to the right there is our airborne magnetometer, and we do thermal sensing. So if there's a need in your community for that, we can supply those kinds of instrumentation to you. And then we've also just in the last few years developed an instrument development laboratory called OPENS, Openly Published Environmental Sensing Lab. And this is designed for users to develop low cost instrumentation and sensors for, again, environmental sensing. The one to the right here happens to be a very low cost dendrometer, which is a technique to measure the change in diameter or circumference of plants, trees as they're growing daily. And we can use these instruments to look at water stress and vegetation. Normally they're very expensive. The idea is to make these things cheaply, quickly, and have users come in and actually work in the laboratory to build their instruments that they need. Like everybody, we have a website. So this is what you would go to. You can request instrumentation. It's quite easy, much like if you've requested nodals from Iris Pascal. You tell us what your experiment looks like, what you might need for instrumentation. If you're not sure, you just put down, I'm not sure. And one of the focus things that we do is we try to work with all of our clients, if you will, to help design distributed temperature sensing or remote sensing experiments in the field. We keep a pretty robust list of publications that are related to distributed temperature sensing, as well as unmanned aircraft. So feel free to take a look there. And then we do training. We do workshops, usually 2 or 3 workshops a year, always at the American Geophysical Union. We'll have a distributed temperature sensing workshop, hands-on. And we also support folks coming into our lab, either of our labs, to work hands-on to get practice with the instruments before they go out. Because recognize in hydrology and in near surface, many people are very unfamiliar with how optical fibers even work. So bringing everybody up to speed has been one of the things that we've focused on, I think, fairly successfully. So I don't think I have to go into too much detail of how distributed temperature sensing works. We do a quick shot of light down an optical fiber, and we are looking in our instruments that we have, we're looking at the Raman backscatter, which is a function of the temperature of the region that the scattering occurs. So, and essentially DTS is LiDAR, is inelastic LiDAR in an optical fiber. Hello, come on, where'd we go? There we go. I think it's okay. Just to give you an overview of the instruments that we maintain, obviously there's a lot of distributed temperature sensing instruments out there. Typically, the instruments we have will measure in a single channel, usually up to 10 kilometers of fiber. They're usually 4-channel instruments, so you can monitor up to 40 kilometers of optical fiber. The instruments we have will resolve temperature differences, typically now down at 50 centimeters. So we're sampling, our spatial sampling is 25 centimeters, and our resolution is usually of order twice that, so about 50 centimeters. We can measure temperature typically for most of our environmental applications. We're measuring temperature averaging over, let's say, a 10-second interval or maybe up to a minute, but we can go down to 1 hertz sampling. And with the instruments we have, we can easily resolve 50 millikelvin differences in temperature, and we can get down to 10 millikelvin quite easily if we integrate longer. So in an environment where the temperatures are changing slowly, more slowly than our sampling interval, obviously, we can get it down to resolution approaching what oceanographers and others are interested in. Everything is field deployable, and we now have instruments that will operate at down to 1 watt as daily use. And that was in collaboration, working closely with actually the folks at Silixa, who I think I saw Thomas this morning on the call. That was a demand for our community, particularly working in polar regions. We really needed to get the power requirements down so that we could leave these things out for through Arctic or Antarctic winters. Again, everything comes back by cell phone to us, data, so users don't have to worry too much about that. And then again, we provide everything that a user would need out in the field for remote installation if needed. So I just want to show you one example of kind of where DTS has been making some fairly significant breakthroughs, and that's in looking in the cryosphere and looking in particularly in the ice shelves of Antarctica and also to some degree in Greenland. And if you're familiar with Antarctic ice shelf behavior right now, the big concern is that the ice shelves of particularly West Antarctica are being melted rather quickly, and these ice shelves actually buttress the much larger ice sheets that lie upstream of the ocean. And as the shelves begin to degrade, these ice sheets that are upstream can become destabilized and essentially fall apart. And we've seen this, in the popular literature anyway, we've seen some of these big shelves calve off. The issue in West Antarctica is because of the topography of the grounding zone of these ice sheets, that once this process starts, it can actually run away, and the entire West Antarctic ice sheet could indeed enter the ocean. And of no concern of the ice that's below sea level, but a significant amount of the ice in West Antarctica is, of course, above sea level. That will cause sea level rise. The challenge is, how do we measure what's going on? Most of the melting is occurring underneath the ice, so from the bottom of the ice, shelves. And this image is greatly vertically exaggerated. The distances here from the edge of the ocean, ice-ocean interface at the sea ice back to the grounding line where the ice is finally on the ground. This can be hundreds of kilometers, typically 100 kilometers, or can be much larger. So how do we monitor what's going on underneath this in the ocean, and again, the melting that generally occurs from the bottom of the shelves? So let's see if we can make this keep moving forward. There we go. So what I'm going to show you right now is some data from a mooring in, this happens to be on the Ross Ice Shelf, where we've drilled through about 200 meters of ice, and we installed a mooring system down through the ice into the ocean below. And in that mooring, in this case, there's multi-mode fiber. There's also single mode fiber, because we want to go back. All of our installations these days include both single and multi-mode fiber. So we can do acoustics on anything that we have installed. And what I'm going to be showing you is then the evolution. The bottom graph here is the ocean. And so this is underneath the ice, under 200 meters of ice, what the temperatures look like. And then the top graph, let's see if we can get this to work, and I can talk through it while it's going. The top graph is actually the ice thickness above. And so this instrument that's measuring as we go along in time, and remember, we're in the Antarctic, so February is summer, you can start to see warm water coming in underneath the ice. These are continuous measurements every meter in this profile. And when I say warm, ocean temperature here is minus 1.9 degrees C normally, and we're getting up to perhaps -1. So that's warm water for Antarctica. And you can see it comes in, and then as we move back into the wintertime, this warm pulse of water, which comes in underneath the ice shelf, is pushed back out due to processes underneath the ice shelf. But what we're interested in is measuring the melt rate of the bottom of the ice. And with DTS, again, our spatial resolution is 50 centimeters, maybe 25 centimeters in a good instrument. And here we're measuring ice melt that might be 1 meter per year. So our spatial resolution is insufficient to capture the melt rate at this particular site. Many other sites are melting at tens of meters over the summer. So normal DTS works fine. So what we did here was we said, well, and this is one of the advantages of DTS, is not just individual temperature measurements, but looking at the thermal gradient and how that thermal gradient, particularly in the ice, how that changes as the bottom of the ice shelf is melting upwards. And so because we get very high spatial resolution, we can resolve the thermal gradient as we approach the ice-ocean interface very well. And from that, we can then begin to resolve where, and we also happen to know, fortunately, the temperature at the ice-ocean interface. It has to be at the pressure melting point of seawater. And we know the salinity, so we know that temperature exactly. And so as a result, we can then map where does that thermal gradient intersect the pressure melting point, and we can now resolve ice shelf melting rates of order millimeters per day. So this is about a little less than a meter over the entire 6 months time period. But we can measure melt rates of a few millimeters per day, which is impossible to do otherwise. No other way to do it. So kind of interesting, kind of cool stuff. Let's see if we can move forward. I just wanted to mention that. So we have another set of experiments that are going on the Thwaites Glacier, which is West Antarctica. Here we have 2 moorings where we have temperature measurements over the last 2 years from the ice-ocean interface, the ice and the ocean. That's been continuous, and now we will be going down this field season to measure. We also have single mode fiber there, so we'll be doing vertical seismic profiles in those moorings that are through the ice to measure ice properties, as well as we hope to look, we'll do some surface shots as well. We hope to be able to resolve differences in salinity in the ocean column below, which is also really important to identify ocean currents and ocean waters that are melting there. So that's ongoing. Just a really quick, we also do, again, CTEMPS also does remote sensing. I just wanted to toss up very quickly that we do topography. This happens to be some work for Lawrence Berkeley lab that we did in Colorado, looking at topography of streams. This is looking down. And then we also do very high resolution multispectral imagery to look at vegetation health. Those are all available. All right, so that is CTEMPS. Let me quickly move on if I still have time. I don't have a watch in front of me, but we'll keep going. Brady will tell me when to stop. A few years ago, from Wang from the University of Wisconsin and Iris Pascal folks and us, we got together and said distributed acoustic sensing is a game changer for earth scientists, and we need to help promote this in the field. And so the National Science Foundation has a program called Research Coordinating Networks, or RCNs, and RCNs are designed to either advance a field or create new directions in a field by coordinating people who are working in that area. It's not designed to do primary research, it's designed to bring people together. And so we started up a year and a half ago with a DAS Research Coordinating Network. Several of the people who are in this workshop today are part of that, and we really appreciate their contributions. And I'm speaking to you about this because I want to encourage you to participate. Many of you on the engineering side may not have been aware of this as much as the earth science side, so please get involved. We have a steering committee. Again, the goals are to bring together the DAS communities, both research, industry, the technology companies and agencies, and see how we can apply and advance applications of DAS in geoscience and engineering. And whoops. Okay, we have working groups. And so again, if you are interested, type into your browser, that last one, just type in IRIS RCN or IRIS DAS, and you will be able to, you'll get right to our homepage. You can contact us if you're interested in participating in these working groups. And while they do say working groups, they're not that much work. So I would encourage you to be part of it. And we're looking for people working in, again, a wide range of earth science and engineering applications to talk about DAS and to develop a community of DAS users. And let's see, my computer's, oh, I see we got, just really quickly, we do workshops, short courses, and webinars. We've got a lot of webinars that are recorded. And again, just go to IRIS and Initiatives DAS RCN. You can grab any of these webinars that have been recorded. We've done virtual workshops. They are also recorded and available for download. And if you're, we typically have a really sort of basic part of this is how DAS works, and then creative new work that people are doing. So depending on where you are in the spectrum of understanding DAS and working with DAS, where you are as a user, there's something there for you. We will be doing another workshop at the American Geophysical Union this year in New Orleans. That is scheduled for Sunday, December 12th. So if you're interested, just go to when you register for AGU, you'll see you can sign up for workshops. And I think the cost is $150, correct? And that will be both virtual and in person. So if you're not going, you can also participate that way. We're also planning to do a field course, a hands-on DAS field course, probably late summer, early fall of 2022. And the RCN does have participant support funds, particularly for early career faculty and students to participate in that. And so if you're, again, interested, please join the RCN, become part of it, and you'll be able to find out when our field course, finally, we were hoping to do it last year, obviously, but we didn't, and we were hoping to do it this fall, but we didn't. But hopefully things will be better next year. And I think with that, I will close it and take questions. Since there's a few fun geothermal talks, I thought I'd throw a picture of a local geothermal feature and its thermal map as well. So thank you, and we'll stop sharing.
Appreciate your time today, Scott. Thank you. Okay, we are now moving into a new segment, I should say, of the the workshop, we're going to start talking about background information for our levee imaging field demonstration. And we're going to turn the time over first to James Lewis, or Jim Lewis, from the U.S. Army Corps of Engineers. He's going to talk to us about motivation for Mississippi River levee research within the U.S. Army Corps of Engineers. So, Jim, go ahead.
All right, thank you. Are you able to hear me okay?
Yeah, we can hear you and we can see your screen.
Okay, great, excellent. So thanks for a chance to speak. I'm just going to give a quick overview of our perspective from the Army Corps of Engineers, focused on the Mississippi River and the system that we manage. So if you're not familiar, the Army Corps of Engineers has offices throughout the country known as district offices, and then it's also grouped into divisions. So the Mississippi Valley Division Office has 6 different districts that are a part of it, and it goes up and down the Mississippi River Valley itself. It starts at the top of St. Paul District, and then the Rock Island District, St. Louis, Memphis, Vicksburg, and New Orleans are the districts that are all within our division. And our division office is here in Vicksburg. It's also right close in the same city to the Engineer Research and Development Center. And so there's a really good relationship in terms of the science and the research that we can perform. I just want to start with the overview of the watershed for the Mississippi River. It covers a lot of states, a lot of area, even part of Canada, and all that water comes down here into the lower part of the system. And it's just a lot of area, a lot of water that all comes down and has to be managed. I want to mention the 1927 flood. So this was a very important flood in terms of the history of the Mississippi River. It was devastating, a lot of damage, a lot of people that died, and a bunch of people that were forced out of their homes, a lot of refugees, and there's a lot of history in that event and how impacting the whole nation was impacted by that event. So 1927 flood was a big event, and it resulted in the federal government deciding we needed to do something at the federal level. And so the 1928 Flood Control Act was really motivated by that 1927 major flood of the Mississippi River. And so in this act, Congress gave the Army Corps of Engineers the authority to do flood risk management on the Mississippi River through this MR&T authority. So it's Mississippi River and Tributaries Project. So just a couple snippets from some of that language. One of the things that it did was it put the Mississippi River Commission and the Army Corps of Engineers together, to work together and perform this task as a unit. And that still happens today. And that last bullet talks about trips up and down the river, and that also still happens. So twice a year, once during higher water, once during lower water, the leadership for the Mississippi River Commission, the leadership for the Army Corps of Engineers get on a boat and they travel down the river and have stops in cities and towns along the way to hold public meetings, allowing folks to voice their concerns and their perspectives about the job of managing flood risk in the Mississippi River. So after 1928 Flood Control Act, the Army Corps of Engineers became much more involved in levees, levee design, levee inspections. That figure on the left just shows how they were designing different slopes for different materials. The top figure shows a cover of a book that was standard instructions for levee inspectors in the Vicksburg district from 1929. That figure in the top right shows construction methods have changed a lot over the years and how they moved the dirt around. That figure in the middle right shows an old sand boil that they were dealing with. And then that figure in the bottom right, I just want to highlight that there's an evolution that's happened in these levees over time. they started with some part of a levee, and then that's grown or been built on over time, so that it's evolved into what it's currently the current form. This slide has a lot of information in it. So the Mississippi River and Tributaries Project is not just levees. There are actually 4 different major features of the MR&T project. Levees and flood walls are, of course, a big part of it. But also there are floodways and backwater areas. So those are listed on the bottom left, numbers there and lists there on the bottom left. And they're also shown in that middle map as well. So at the upper end of the system, the MR&T system has a geographical extent to it that starts at about where the Ohio River and the Mississippi River come together. And there's a city there called Cairo. And the floodway that's right there at that location is called Birds Point, New Madrid floodway. And that one is kind of a release valve to have flow come off of the Mississippi River. And the key with that one is the timing. So the water that comes into that floodway ends up back into the river, but it is intended to knock the peak down. So that one is all about the timing to take the peak of the event lower in the system. And then as you walk down the system, there are backwater areas. And these backwater areas are intended to give the river room. As the extreme flooding happens, these are locations where it's intended to flow out of the river and into these areas to take water. So there's a St. Francis backwater area, White River backwater area, Yazoo backwater, and a Red River backwater. Those are all locations that during the project design flood event are intended to help, manage that extreme high flow. Then as you work down the system, there's the Old River Control Structure. That's a structure, a set of structures that manages the distribution of flow between what goes down the rest of the Mississippi River and what goes over to the Atchafalaya River. And then a couple more structures here to mention. The West Atchafalaya floodway, that one hasn't been used and probably wouldn't be used. Since it was constructed, the river has degraded in that location so that the floodway is kind of perched or higher than we would expect the water to get up to. But as you move down, you have the Morganza floodway, and that one is operated so that anything over 1.5 million cubic feet per second would go through that floodway, and then anything over 1.25 million cubic feet per second would go through the Bonnie Carey spillway, which is the next one there, just above the New Orleans location. And so in that table on the left shows the different frequencies of how often they've been used. The top right figure is the 2011 flood, and you see the levee. Let me see if I can move my cursor. You see the levee top there. You kind of see the road line of the top of the levee. And then on the land side of it, that area near Baton Rouge, a lot of value in that land, and you can see how high the 2011 flood got during that time. The bottom right is of the Bonnie Carey spillway. So flow in the river is going from left to right, and then that dark line is the structure itself, which allows flow from the river to reach Lake Pontchartrain in the background there. And then this is my last slide. So the Mississippi Valley Division has a science program known as the Geomorphology and Potamology program. And potamology just means the study of rivers. But through that program, we perform a wide range of science. And that Levy research that you'll hear about in later presentations is funded through this program. We recently completed an assessment that we called the Flowline Assessment to calculate what the water surfaces would be all the way through the system for that project design flood event. And we also track sedimentation trends. There are spots where over time for the same flow rate, water surfaces are going up, and other locations where the water surfaces are going down over time. We also look at the basin changes in land use and water yield. The top right figure shows a numerical model example of how we're improving our tools to simulate hydraulic and sediment behavior. And then that bottom right figure just shows how we have threatened and endangered species that we work to improve their habitat values. But the levee research is important. So during a flood event, there's a lot of activity that we as the Corps perform to monitor these thousands of miles of levees that we have and inspect them and look for seepage concerns, potential sand boils, and deal with those. So I hope this overview of the Mississippi River and motivation for levee research has been interesting. List my email address, and if anyone has questions, feel free to reach out to me. Thanks for the chance to speak.
Thank you, Jim. Appreciate it. And tomorrow on our way up to the levee, we'll cross or go right past the old river control structure that Jim mentioned. And so you'll get the chance to see that as well. Jim, thank you for your time today. We're going to transition to an in-house speaker here, Professor Bob Gilbert from the University of Texas. He's actually the department chair of the Civil Architectural and Environmental Engineering Department at the University of Texas. He's going to speak to us about observations of, from the lower Mississippi River flood in 2011.
Thank you, Brady. Yeah, so Jim's talk is a great lead into this talk. So this is what we saw happen in the Mississippi River 2011 flood. This is the product. Okay, it's the product of a group of people that did some reconnaissance supported by the National Science Foundation through the DEER program, as well as collaboration with the U.S. Army Corps of Engineers. And we produced a report in 2011 about this reconnaissance. There we go. Okay, and here are all the people that were a part of this. And I'm just going to tell you some of the things we saw, many of which are close by to here. So here are flow rates, peak flow rates through the system during this event. And the thing to notice is if you look, for example, at Vicksburg, the flow rate is the highest we've seen and the highest since 1927, even higher than what happened in 1927. So the system, for much of it, was loaded beyond what it had ever been loaded before. The places we're going to look at are the old river control structure, the Morganza Spillway, and then right here near the LSU campus at Duncan Point. And here's the old river control structure. In 1973, this was built in 1964. That center gate is the main part of that structure, and it separates the flow of the Mississippi. 70% stays in the Mississippi Channel and 30% goes into the lower Atchafalaya. Under normal times, when there's a flood, they start sending more water into the lower Atchafalaya. And during 1973, they were sending water into that through that structure, and a 30-foot deep scour hole formed at the toe of that structure, and there was a distinct possibility that they could lose that structure during that event. So they added the auxiliary spillway above that in order to try to control the flow rate going through that structure. But it's a significant structure because if you lost control at this point, you essentially lose control of the Mississippi River, and it would bypass Baton Rouge and New Orleans. So here is that control structure in 2011. It performed well. It performed in the way it was intended to perform. So that was a good news story here. The Morganza Spillway is a little bit further down. And here the Morganza Spillway, again, is at pretty much its capacity in terms of discharging into the Morganza floodway, which is about a 5-mile floodway before you get back to the Atchafalaya River. And again, this structure in this particular event performed well, but there, dealing with very, very high flow rates, very significant potential for erosion. And so understanding what's going on in these structures during these events is a very important part of making sure that things are going to go well. And then when we get down here near the LSU campus, here's what the levee looks like. This is on the east bank of the river. The flood levels along this stretch of levee in the vicinity of the campus and going all the way up to the old river structure were at the freeboard. So they are at the highest level that's intended. In some locations, it got above the 3-foot freeboard, and so they were adding sandbags and HESCO baskets on top of it to increase the freeboard temporarily during the event. And you saw a schematic of what these levees generically look like. I'm going to talk about what's underneath them. So there's a blanket layer that's fairly fine-grained, and then there's some more coarse-grained materials, and then a substratum sand layer. And so what we worry about is the seepage going through those layers underneath these levees, potentially causing internal erosion or potentially causing instability. And here's an example of that seepage. Just happened there. So there's sheet seepage is the best example where the water is coming under a fairly low gradient. It's not concentrated, and it's basically just coming to the surface at the toe and beyond the toe of the levee. So here's an example of that. This is just north of where we are right now, and you can see that field is filling with water, but there's not a concentrated flow through a particular feature. The next feature are these sand boils that Jim talked about. So there were about 30 of these that developed along the system during the 2011 flood. During the flood event and the flood fight activities, what they do is they either pile sandbags or they put barrels on top of these sand boils so that the ground surface has a water head on top of it at that location, which slows down the flow rate. It slows down or reduces the gradient and hopefully reduces the erosion that's occurring. You can see here one where they've placed the barrel, and another one that right after we were there, they put another barrel over that sand boil. These are interesting. They're right along the line of a utility. And so we don't know if maybe there were utility poles that used to be at these locations that they've removed, and that something that we did put holes through that natural blanket, or if there are natural features that cause them. One of the interesting things about this flood event was that there were locations where they've had sand boils before, and we found sand boils again. There were locations where they had never had sand boils before, and new sand boils formed. And then there were other locations where in the past they had had sand boils, and sand boils did not form in this flood event. So it's not only variable spatially, it varies with time. And then there are some of these distant sand boils. These were really interesting. This is 3,000 feet away from the levee, just south of here on the east side, where sand boils formed. And, you know, it's not that big of a deal, potentially in terms of the stability of the levee, although obviously water is going, and if you've got piping, it's over a large distance away from the levee. But these sand boils can form in areas where there are other things, like here is a berm that supports a pond. So potentially that berm could have been undermined. And here we're 2 miles away. This is on the west bank, but 2 miles away from the river. You have dry land. We drove over it. We get to this point, and the water has popped up and actually taken out a road at this location. So it's a really, really interesting geologic setting that we're dealing with. And the way that they try to address problems where they're getting seepage or they're getting sand boils is they extend the width of the levee with seepage berms. They put relief wells down into that substratum sand, but it's very much of an observational approach. They see where there are problems, and then they put these features in to try to improve the capacity of the system based on what they're observing. But it would be a much better approach if we could figure out what's really going on in the ground and be proactive about making those levees as strong as possible. So in summary, we had a historic system, or a historic load on the system. It performed very well. It's spatially variable though, it's temporally variable, and I think there's a lot of potential for what you all do that could improve our ability to make it a better system. Thank you.
Thank you. Okay, thank you for that, Bob, for helping us set the stage. We have another presentation up next that I think will go further to set the stage for the specific section of levee that we're talking about. We have Brian Jordan, who's going to speak to us. Brian is with the Vicksburg District of the U.S. Army Corps of Engineers, and he is the Analytical and Levee Safety Section Chief for the Vicksburg District. And so Brian will be talking specifically about the section of levee that we'll be visiting tomorrow.
Right. Yeah, that's not it. That's all right, I'll find it.
They all have very similar names.
I already hit escape. I didn't want to listen to me.
I would have liked to see.
I look like it. I mean,
That's Blackhawk.
That's,
Yeah, no, that's the. And I unshare. Oh, yeah.
well, I don't know who planned out the sequence of these presentations, but that was incredible having Jim and Bob. Is that who it? That was absolutely perfect timing because those both set the stage really well for this presentation. Since Jim did such a great job giving us an overview, I'm going to do a very mediocre job of getting in the minutia. So we're going to get really specific on the site that we're going to go see tomorrow. All right, so my name is Brian Jordan. I work for the Vicksburg District Army Corps of Engineers. Seeing pictures of the 2011 flood makes me very tired. I spent a lot of time walking levees and building sandbag rings that year. So
slide should advance, hit the down arrow, it just takes a minute for some reason. So.
well, we're not too far from here tomorrow. We're about 40 miles southwest of Baton Rouge, Natchez, Mississippi, and more importantly, about 10 miles north of Old River Control Structure. I have maps to show you this that will come up here in a moment.
Takes a long time.
Yeah.
Well, there you go.
So the site was discovered in 2016 by, or was reported to us by a landowner who owned a fishing camp on a landside borrow pit that was used for the previous enlargement back in the 50s. We don't do landside borrow pits anymore, strictly because it creates the kind of situations that we saw in this particular site. Are you sure it's going to? Okay.
You get the down arrow or the space bar?
Either one, right?
Yeah, try the down arrow.
I need a clicker. I need a clicker with a laser beam.
You might have to click back on the presentation.
Yeah, we got that. Then I'll run that's on that, and then.
That's where we are.
Okay.
As you can see, Natchez up north. It's pretty far north of Baton Rouge from here, and then directly east of Alexandria, Louisiana. This is really the what I wanted to kind of get in on. The important part of where the location is, because any kind of breach along the Mississippi River levee is an issue. But this one was 10 miles north of Old River Control Structure. As you see, just to the west there is the Atchafalaya River. So you can imagine that a breach on the mainline Mississippi River levee at this location would dump water directly into the Atchafalaya. And there's also quite an elevation difference between those two. So there was a potential, and God, we didn't even get close to realizing this potential, but there was a potential of partially and temporarily rerouting the Mississippi River down the Atchafalaya. On it, obviously, it got a lot of people's dander up. So we were sent out to take a look. And as you can see, that's very telling. There's a sand boil that's lipping the top of the water. You could actually watch the waves break on the sand. And as you got on top of it, you could actually see the material rolling in the throat. We sent a team of surveyors down with some multi-beam drone boat. We got this imagery. As you can see, it's obvious, right? There's a large sand boil. This pit was 8 to 11 feet deep. So that is a 8 to 11 foot cone of sand with a delta. So, you know, in the terms of sand boil language, it's all about material. That's why we put the sandbag rings and the barrels around them, we don't want to stop the water flow. Water flow's fine as long as it doesn't move material with it. This is a lot of material. So we put the mechanisms in motion to develop a design to remediate this area, get it fixed, put in funding, hire a contract, all that kind of stuff to fix it. Unfortunately, Mother Nature had other ideas, because soon after this imagery was taken, we got word that there was a major flood event coming. This was a flood of 2018. And it was going to be comparable to 2011. It didn't turn out to be that comparable, but it was a major flood event. And at the time, they said it could be in the neighborhood of 2011. Sand boils get worse with each subsequent event. As you move material, that substratum gets more and more loose, it transmits more water, more velocity, more material movement. So we knew, given the location and given the situation, that we needed to do something, and we needed to do it before this flood wave hit. Luckily, with the Mississippi River, we had time. We had about 3 weeks to plan and execute our remediation. So we started off with, what are we dealing with? You know, the geology. We went and looked at some tertiary borings and geological map. So you can see we're in a back swamp area that has got a lot of natural levee, not your usual sand boil location. And the boring you see there on the right gives you another indication that we shouldn't be seeing boils in this location. It didn't make any sense. That top stratum was 25 to 38 feet thick. Usually that's all you need and you're fine. You'll never put a relief well, you'll never have to burn, it'll be fine. And yet here we had this massive sand boil. So we sent our CPT crew to go push some cone penetrometer tests, for those of you who don't speak the acronyms, at the landside and riverside toe. And this one caused a couple of hats to drop. Those are sand layers that are 5 feet below the ground surface. What? This would cause a serious seepage issue. But it did not make any sense when in conjunction with the sand boil we saw. That the elevation of the effluent of the sand boil, like down there at the bottom of that pit, was well below these layers. So, you know, the water flows down in elevation, then up. Didn't make a whole lot of sense. So we did something that we typically don't do, and we pushed a CPT through the center line of the levee. We don't like messing with the levee section itself, but in this case, it seemed like the right thing to do. And thank goodness that's not what was going on. There was these sand layers were only found at the toes and not in the center line. So it was not continuous. The best we can figure is when they designed this, they were having problems meeting their stability requirements. And they decided the best way to get around that, since they had such large top stratum thicknesses and probably weren't going to have any seepage issues, was to add sand and gravel stability buttresses underneath the wings, so to speak, of the levee. Still had no idea what was causing the boil until the surveys came back. The cross-sectional surveys gave us an elevation at the bottom of that pit. We compared that to as-built crest and landside toe elevations as constructed, and we realized what we were actually dealing with. 40 feet of head across a river levee. This is not something that we're typically see at all. And as you see, there's a there's a lot of difference in elevation between the riverside, the landside toe in the bottom of that borrow pit. So you're losing some of your top stratum there too. So not only do you have 40 feet of head, but you also have a reduced thickness in your top stratum. And that was the magic key to the equation, because when we started putting that into the analysis, it started showing us that in 2011, we actually would have gotten heave. And once you get heave with that much head and you have a fracture, or you have a defect, then KD bar the door, all the safety of the world's going to come through until you do something about it. As seepage goes, you have a couple ways you can deal with it. With sandbag rings, you can equalize the water pressures, right? You reduce the differential head across your levee's cross section. That was certainly something we looked into and something we ultimately did. We built up a small levee around the bar pit, but we weren't able to get a whole lot of water stacked on it. We didn't think it was enough. Not to mention, if something happened to that line of protection and it blew out, all of a sudden you would have a huge increase in head differential and could cause a real problem there too. So what we decided to do was to add material on top of the sand bowl location. Now we said sand right here, but frankly, we would have used any material available. We just needed weight. We needed that overburden weight on top of that location, so that seep water can bleed off without actually carrying any material with it. We capped that with 57 stone. This was something that was used to great effect during the 2011 flood in some real bad sand boils close to the levee. In I think Winterville and somewhere else. They basically dumped a filter down the throat of an active boil, and it worked a treat. It stopped the material movement, clear flow. So what we were thinking with that is, worst case scenario, this thing blows up or we have a project flood before we can get the final remediation in place. This is there to fall into whatever opens up and actually filter the exit possibly. Yeah. But we were really after the weight. So where do we get the material? We looked around. You're in the middle of nowhere, and Louisiana is flat. There's no hills to go crop and get material from. So we were caught between a rock and a hard place, so to speak. We couldn't dig another hole because that's how we got in the problem in the first place. So what we landed on was this large sandbar across the river. So now we had a plan, we had a design, we had a plan. So we developed an emergency contract, hired some contractors with the aid of our own hired labor crews who do a lot of slide repair and menial jobs for us in the Corps. We got to work. It was a mess. It was an absolute nightmare. It's the exact opposite of the 2011 flood. 2011 flood, we had a drought. Everything was dry. You could drive anywhere you wanted to. This was a sloppy nightmare. The only silver lining was that there was a training dike across the levee from the site that the barges were actually able to pull up to and unload on. But it was silty material and rutted, and we ended up having to use triaxial geogrid to give us a foundation we could drive on. That's actually underneath this entire site now and forever. That's them unloading off the barge onto the large. We use large off-road dump trucks. Had a hard time maintaining the roads until we went full bore and just dumped A-stone from Old River structure everywhere and just drove on top of it. There you can see the A-stone that the trucks are riding on. That's them constructing. You'll see that on the right there, that's the dike we were using to offload. Well, the river is coming up. So we started losing our dike. And so we literally just had to march the offloading operation closer and closer to the levee until they were actually unloading the sand barges directly onto trucks onto the levee. And there you can see, and I get an idea of the flood loading we were looking at too. It was a substantial flood loading. That's the finished pad. That white dot there in the middle is about, well, you actually can't see the white dot in the middle. There's a white dot in the middle right there. That is the sand boil location. We basically tried to center up this entire pad around that and then centered the 57 stone on top of the boil itself. That's the finished product. And as you can see, the effort to bring the water up in the bar pit actually worked pretty well too. Wasn't much effort done there, and it gave us about 5 or 6 feet, which bought us time to get the rest of it finished. And that's the scary one. So that's really what the situation was. That's the Mississippi River in the background there, and the bar pit in the foreground. That's how close we were. Happy ending for sure. Everybody did an amazing job, right from the contractors to our own guys to the contract experts that back at the district office did amazing. I mean, they were working 20-hour days. I felt so bad for those guys. But it all got done in the course of, I think 12, 13 days, we went from nothing to a finished product, which was quite astounding. And it was done before the crest. And we had no signs that it had moved since. So since then, we've installed relief wells. So we are very confident that there will never be an issue at this location again. They're going to arrest if there is another sand boil, the relief wells will arrest any kind of progression to the levee.
Wow. Brian, thank you for the presentation.
Sure.
Super interesting. I was out there yesterday. I saw things, but seeing what was going on and how you fixed it, it's sobering. And I look forward now to going back tomorrow and looking at things in kind of a new light. And now that I've seen kind of the background information. So those of you who are participating in the tour tomorrow, you'll get to see the gravel blanket, the relief wells, you'll see where the fiber's at and stuff. So very excellent. Thank you, Brian.
Thank you.
Our next speaker is Dan Costley. Dr. Dan Costley, Richard, as he is formerly known and named by his parents. I learned something yesterday about Dan. He did his undergraduate and master's degrees at the University of Texas, so we had some commonality, which was really interesting to learn about. And Dan and John Murphy are the ones who are in charge of this research project, their practical research project at the Black Hawk site, looking at distributed fiber optic fencing with some help and support from the Berkeley.
Yeah.
Earlier.
Okay, can you get rid of that thing at the top as it comes up?
Yeah, I'll hide it.
Oh, looks like it's not there.
Well, it's because I haven't shared the screen yet.
Okay.
Maybe hit next slide now.
Yeah.
Well, I also have to change settings so it actually streams the slideshow.
Okay.
So I think it might actually be the screen sharing that screws it up.
Oh, okay.
So we'll find out.
Hello, I'm Dan Costley. As was mentioned, I'd like to recognize my partner in crime, John Murphy. So I don't have any background in geotechnical engineering, and John does, and so that's what makes this work. So, and we're going to talk about what we did at the Black Hawk site, and you're going to see some of the slides that I pirated off of a previous presentation by Brian Jordan. So appreciate those. Yeah, so those two pictures are from John. You recognize those at the far end. So I mean from Brian. Okay, I hit down. Just hit it. I should have hit it a half hour ago, right? Okay, so the first slide talks about the original research hypothesis and basically this was funded by Jim Lewis's Mississippi River geomorphology and potamology program, and we had written a proposal and they told us it was funded, and we were thinking about where we were going to put this project, and then Jim said, "Thou shalt put it here." So, and we didn't understand, but now we have a pretty good understanding why it's here. So the research was whether we could monitor seepage and uplift with the fiber optic sensors, with distributed fiber optic sensing. Okay, there you go. And so we were going to look at, originally we were just going to look at DAS, distributed acoustic sensing, and I had some experience with DAS and MASW. I knew that could tell us some stuff, and also with passive sensing. I didn't know if it would detect groundwater motion or not. Probably not, but maybe burying animals in the levee at some locations. I've heard that's an issue. And then we met the folks at UC Berkeley, and they're involved with the project. You'll see later. We thought that the DSS has an application here with the distributed temperature sensing as well. So the approach was to install fiber optic sensors at the site, and we also put conventional sensors in there for validation with what we're doing. So this is the picture I stole from Brian, and there's, you see the sand boil site, the Mississippi River. So there's a highway on the levee, Highway 15, and there's a site from the gravel pad. So, and Brittany and I and Mung were there yesterday, and we saw an alligator, and we ask you not to pet the alligator if you come out tomorrow. So and that shows the map with the Black Hawk test site in relation to the Old River control structure. This is, well, I'd put this together, but it looks a lot like Brian's slide. I didn't steal this one, but you can see where our site is in relation to the Red River here, and that's, I think, why the property owner got so nervous. And there's the, oh, I'm supposed to stand behind there, and in relation to the Old River control structure. So Brian mentioned the relief wells they put in. So when we first started going down there, they were just going in, but there a row of a dozen, baker's dozen relief wells along the side. You'll see them. They're yellow, and when the river gets to 40 feet at Natchez, they're flowing, and it's, I've tasted the water out of them. It doesn't taste good. I thought it'd be pretty fresh. It tastes like sulfur, so don't do that. So we do in the sensing, we're doing DSS and DTS, as I mentioned, and the DAS, we're going to see what we find out from the passive, but also with the active seismic. And I think we're going to get more than we bargained for tomorrow with, and yesterday with all the data we took and that we're going to take tomorrow. So, and there's another view from the gravel pad back toward the levee, and that's kind of where our our instrumentation shed. I don't think it's there yet, but in this picture, this is a couple of years old, these photos. So, so earlier this year, we had a heck of a time getting things installed. We're probably a year behind schedule, what with COVID. And then, well, as I mentioned, I'm not a geotechnical engineer, and I'm not a levee expert. And I learned there's a thing called permits. So we had to get a permit from the levee, and so that was a long, involved process. But then also the COVID, people really don't like it when you dig holes in their levee, we learned. So, so we went out there anyway. It was wet, and we tried to first start to trench the thing. We had a different fiber, and that didn't go well because it was clay and it was clogging up, and our trencher wouldn't go. And then the text said, you know, we could plow this in a day. And so we switched to our cable, to the armored cable. And truly enough, they got it done in a day. But you could see, so there's, you saw in Brian's slide, there's kind of a bench or a shelf, and then there's the lower part next to the thing. At the lower part, it was real wet, and you see times they had the skid steers pulling the plow. So we plowed it in, so the cable's coming up here and plowing in. So you can't have it. You have to have a pretty strong cable, it has to have that strength. And so he's pulling it back there, you kind of stuff. But once you got on high ground, it did really well. And there's the cable on the far right. And there's then the finished product. I think y'all are going to get these slides up. One thing, so when you look at the data, maybe you could make some sense of it. So the cyan line is the actual path of the fiber. So you got the lower part that goes next to the relief wells. It looks like it runs right over them, but the GPS for the relief wells with just the handheld, so it's not as accurate as the cyan line. So it runs to the right of them as you're going this way. The numbers there are the meters out of from the instrumentation, and we had an instrumentation shed right here. It's called a Tricon. It's an Army thing that it was surplus, and we used that our instrumentations in there. And these numbers are the meters from the Tricon. So down here we've got 518 and 543. We go back here 14, 46, 504. Those, just keep those as reference. It comes back to the bottom, to the southeast side before it goes back into the Tricon. We have 2 boreholes that we drilled. We're drilling 2 more next week. That should be fun. So that was one on the shelf and one lower here. I'll show the profile for those a little bit later. John and his cohorts put in these water level sensors. We know the water gauge at the Vicksburg, and I imagine there's other gauges downstream, but here we can keep track of it on site. Jim Lewis actually had some, I guess, surplus, and he offered those to us, and John saw the need for them, and we took them out. So they're on the end of that gravel pad and one on the river side, so we can know where the water level is. So, the current boreholes are here, and they're on a 7-block line that comes into the Tricon. We're going to put 2 more boreholes next week. So y'all seen this before. I'm not going to spend too much time. We have access to 2 interrogators. The one that we're using tomorrow, though, is not ours. It belongs to those. It's a newer model, OptiSense ODH4. We have a updated version of the ODH3 that we took data on, Peter and John and I, a couple of weeks ago. And the Naval Research Laboratory, that we have access to that. We haven't used it at the site yet. That has adjustable gauge length, 2, 4, or 10 meters. I just put a plug in. That group at Naval Research did some of the original work in fiber optic sensing. They invented the fiber optic microphone in the 70s, which is used in the fleet today for Navy is interested in underwater sounds. Okay. Anyways, but they also do this now. Okay, so this is, we were there a couple of weeks ago, and with the RODH3, and Peter had set up, and this is, we took this waterfall plot, except it's laying on its side. So here's time, it's 12:31. This shows a tanker truck driving along the highway. It's going north, so it hits 500. Remember, 500 was on the southeast and leads northwest. So this is the fiber that's on the response on the bench, and here's on the lower side. We put a 3-axis seismometer on the crest of the levee. It's about this location. I should have gone back. Can I? It's right here, the seismometer. About right here. So it's about 950 meters or so. And you can see, just as a reference, half a millimeter per second is the amplitude of the thing. It's a 3-axis, and you can see the spectrum that we're getting. So, and here's a smaller southbound vehicle. At first, I thought it was pulling a trailer, but then I looked. There's about 10 seconds between them, and at 60 miles an hour, I figured out it's like 260 meters, and so that'd be a pretty long trailer. But so I figured it was smaller car following a truck. So, but that's and I think Peter has some interest in using sources like this for to do the MASW type and to get the sound speed profile. So that so Dr. Soga showed this. I didn't take these from him. We must have stolen from the same place. But anyway, where you can, this is their interrogator. So basically, use a Bruin. I'm just going to mention that the cable, I guess it's 2 separate cables. It has a loose tube and a tightly buffered, so that we could track the temperature from the strain and get both strain and temperature. There is, I also want to mention the Berkeley guys, along with John Murphy, designed the borehole and how we were going to do it. John came up with a great test plan. There he is. I don't know how he manages to stay clean. So there's the business end. So you got the fiber and it's wrapped around this, I guess, this thing, this trimming pipe. So the fiber goes down the pipe and back up. So actually there's, you got 2 tightly buffered going down and then, or just 1, right?
1 DAS tightly buffered, and then our DSTS has strain down, temperature up.
Yeah, so we got a DAS cable down there, and then the DSS DTS cable, so we can do that. And so this is trimming pipe before they put it in. Then they put it in, and they keep adding sections of it's basically PVC pipe. And there's the end result on the far right, and with the box and ready to put the clamp on it, so that when they come and mow the levee, that it's not going to bother our stuff. So, and there's a schematic of also within that pipe. We got some piezometers to compare, and I think within the piezometers there's thermocouples, so we can measure the temperature and the pressure both at the bottom of the hole. So the bottom of the cable or the bored hole is approximately 100 meters below the ground, but they're both all designed to be, even though there's some higher on the levee than the others, the bottoms they designed them so they're going to be similar all the way down. So, and that's when the cable goes downhill from there into the tripod. So both of these both boreholes are on the same cable. And when we do the other boreholes, they're going to do the same thing. It's all be on the same cable and go down the slope. And on the bottom right is the baseline DSS measurement that has the temperature taken out of it. So future measurements after a flood event, or when the water gets high, we want to know if the water is pushing up on the clay blanket. Can measure the strain. We'll subtract it from this. So, and I think I rushed through my talk, right? So but that's good, right? I would like to acknowledge the Mississippi River Geomorphology and Potamology program who's funding this work, and Dr. Jim Lewis, he heard from him earlier. Our partners, the UC Berkeley, and mentioned them. Ling Ching, I think, built the interrogator. James Wong spent the week out here. Peter just seems to come when the weather's nice, and Li Ching was here when it was hotter than Hades. And Andrew will be here next week. So, and we've worked, OptiSense has worked with us. They rejuvenated our ODH3, and I think we are interested in getting their strain module and comparing the results we get with that with what we get from the DSS. I want to thank John's branch at ERDC, the geotechnical engineering and geosciences branch, and the whole list of people in there, technicians and engineers that helped. And the Vicksburg district and the 5th Levy board helped with the permitting, and actually just given a lot of information about that was useful. And Dr. Maureen Corcoran, who's a geologist in my lab, GSL at ERDC, and she told me about the opportunity, and helped me write the proposal and reviewed it and rewrote it and read. Geez. So anyway, so I think we're ready to.
Excellent. Good. Thank you, Matt. Appreciate it.